Welcome everyone to lecture 17. This is a transition in the course. The way we are going to approach data science, the problems that we are going to address, these are going to be reflective of the kinds of problems we'll address from now on. But first, homework as usual, early turn-in as usual. The midterm by now, you know, it's in Friday in 2 weeks, and those are the ed posts which have all the logistics and so on and so forth. The scope is everything through chapter 12, which is everything we'll teach. I should tell you something about chapter 12, which is the main method will be covered this Friday, and then there are some additions to that method that we'll do on the following Monday, and then Wednesday will be just a slew of examples on 11 and 12, and Friday is a review lecture. So it's not as though you learn. Sorry?
Are you sharing your screen, or supposed to be?
Oh, whoops. Thank you. Let's try that again. Let's try that again. Oh, that looks much better. Sorry about that. Okay. So homework, midterm, scope, and if you need to take the exam at an alternate time, then you should have filled out the Google form. But if you haven't yet, then please email the address on your screen by Friday. Okay. So the goals this week, we are now going to start talking about trying to explain the data that we're getting. For the last couple of weeks, you have had examples where we've been rolling dice, and in your homework, you're playing roulette. And last time we drew from a population of, I think, airline flight delays where we had all the data. And it kind of seemed like a game. We were understanding how random samples behaved, but it did seem a little bit like a game. But these methods are extremely powerful. And so now we are going to try, from now on, we're going to use those methods to try to explain the world. And so today we'll assess the consistency of the data and a model. I'll explain what that is. It's a set of assumptions. We'll, in a couple of contexts. On Wednesday, we'll set out the terminology and the general process of what we are going to do in particular cases today. That terminology and general process will be used then consistently afterwards. And on Friday, we will just start exploring a different setting in which we assess models. Now, some of our lecture today and Wednesday might go over slightly, but we should be okay. By the end of Friday, we should be where we intend to be. Okay, so the word model, a model, you know, if you've built anything as a model as a child, it's a simplification of reality. In data science, a model is a set of assumptions about the data. It is our attempt to explain the data. And, you know, the world is infinitely complex. We try to give an explanation that is sufficient to more or less explain what we are seeing, but we are very well aware that we can't capture every single detail. Okay, so we have some explanation in mind, and many of the models, many of the assumptions that we're going to be making involve randomness. And these are called chance models, models involving a random selection somehow. But you can have any set of assumptions you want. In the end, you have to compare it with the data. Right, and so the key question is this set of assumptions, does it look reasonable for the data at hand? And that's going to be this type of question that we address from now until the end of the class. So we should also, at some point, we will say, okay, I believe this model, but there are some unknown quantities in this model. Can I estimate them somehow? So all of this is called inference, right? You have some data and you have a set of assumptions and you're trying to see whether the assumptions make sense based on the data. You're trying to go back to explaining the world based on your data. And so the approach is, if our assumptions are about random selection, well, we know how to select randomly. That's what we've been doing for the past 2 weeks. So why don't we just select randomly? Why don't we pretend the world is the way we're assuming it is and just select randomly? Then we can see what our assumptions would predict. If the world were the way we are assuming, then what would happen? That we can see. And then we can compare those predictions to the data that we observe. And now you have prediction here and data there. And if the prediction is here and the data are there, then they're far apart. And it doesn't look like the predictions made sense, right? So the assumptions behind our predictions don't look justified. That's kind of the approach that we are going to take. And we're just going to do it in a succession of examples. I want to make the point again that the examples that you have had thus far are about games of chance and sampling from known populations, but we are going to use those methods in settings where your calculation is actually going to have quite a lot of impact. And so somehow I have lost my screen. Okay, here we go. I want to talk a little bit about today's examples. So these are examples to do with data science in society, data in society. And so therefore, they are not merely calculations. They are a look at how our society works. In particular, we are going to approach the world keeping in mind some goals of the field. What is data science for in the end? It is to understand the world better. And why do we want to understand the world better? Because we want to improve things, right? In the end, that is what data science is for. It's not just for doing calculations. So the example that we're going to take of this setting is we are going to see how data science can help expose injustice, significant injustice in the world. And therefore, how data science can then be a tool for countering injustice. And one of the reasons for choosing the examples that we have is that you will see that you, just 7 weeks into your first data science class, already have skills that empower you to do this quite significantly. There's a second reason that I have for the examples. I'll talk about that after we've gone through the first one. Now we're going to be talking about bias. We're going to be talking about racism. We are going to be talking about pain. And so we will breathe, we will take a moment and we will discuss. And what I would really like all of you to do is to feel free to stop us and to ask your questions and discuss. We don't have a particular set time. We will just talk through anything that you want to discuss. The first example, in fact, both of them are about the law. So the US Constitution grants us all equal protection under the law. In particular, every defendant, everybody who's accused, has a right to due process. That means the prosecution and the legal system must follow the process to which the defendant is entitled. Because if not, everything else is invalid. And so these are two examples about due process under the law, and at two very different times in history. The first one is a US Supreme Court in the 1960s in the US South. And so, we will talk about how at that point there was a lot of prejudice, segregation, injustice, racial injustice towards Black people. And in this example, a Black defendant was simply denied his constitutional right to a fair jury. Now, of course, the courts didn't think so. The courts provided a verdict, and the US Supreme Court, in our view, made incorrect and biased judgments about not only the data in the case, but also the legal processes in the defendant's original trial. So we will discuss how you, as new data scientists, can address this. We will discuss the bias, and then hopefully, once we've done that, we will talk about how we can use the questions raised by this example in addressing the decisions and the approach that we have to life in the present day. It's important to note that, this case became the foundation of reform. And it is very, very important to note that the strength and the persistence of people who struggle becomes the basis of a betterment for the rest of us. And so respecting that struggle is a very important part of understanding history. And then what we'll go on to is another example, which is more recent. So now in the 21st century, things are better. They are better, but they are still flawed. And there is no question that the events of the past 2 years have reminded us that there are flaws, significant flaws that we should address. What we're going to do is we're going to take an ACLU study of local jury selection. Alameda County, around about 10 years ago. And the report says that the jury pools don't reflect the composition of people who live in the county, which was kind of the same issue in the Supreme Court case in the first example. And so we'll discuss the reason for the differences and possible improvements in the process. So what I'm going to do now is pause for a second before we launch into the example and ask if there are questions on the chat. So what do you think? Should we get started? We'll discuss where the data comes from in some detail. Right. So to understand the issues, it is important to understand how juries are selected. And something has happened here. Let me try that again. Okay. So the Constitution grants everyone a right to a speedy and public trial by an impartial jury, and the key word there is impartial, right? So the jury selection process works like this. Wherever the trial is being held, there is a definition of who is eligible to be a juror, right? So in Alameda County, you have to be over 18 years old, you have to be able to understand English, you have to be able to travel to the location of the trial, and so on and so forth. There are criteria for juries. And that's a huge population, typically. From those, a panel of possible jurors is selected. And it is this panel that is supposed to be representative of all the eligible jurors. Right, so the word representative has multiple interpretations for us, looks like a random sample is a good interpretation. So it is this first arrow where you're looking for the panel that you select to be representative, and the panel may have about 100 people in it in certain kinds of trials. And then from that, the judge and the lawyers on both sides select a jury of 12 people, and that is not random at all. That is, you go in, you fill out a questionnaire, and then there's a question and answer period, and then there's some deliberation, and then 12 people are selected. This portion is not random, but this portion should at least look like it was a random sample. That is the background. And so the Supreme Court case now is a case of a Robert Swain, who was a Black man convicted in Talladega County, Alabama in 1962. And he appealed, saying that not only was his jury selection unfair, all juries in the past 10 years in Talladega County had a very small percentage, all jury panels had a very small percentage of Black jurors. And if you look at the eventual juries, nobody was Black. And so the data that you are seeing now are the data in Robert Swain's own trial. So at that time, in Talladega County in Alabama, only men aged over 21 could be jurors. Of that population, 26% were Black men. But in his panel of 100 people who were supposed to be representative of the eligible population, 8 were Black. Now remember, representative is an important word. If your jury panel is not representative of the population of eligible jurors, then your trial may not be fair. At the second stage, this was not random selection at all. This was deliberate exclusion, and we will talk about that separately. But first, let me ask you a question. The court denied Robert Swain's appeal on 2 grounds. He had multiple grounds in his appeal, and there were on each ground, the court said no, no, and no. This is the US Supreme Court. And the US Supreme Court made a statement about that initial selection. You have a population where 26% of the eligible population is Black men, but on your panel of 100 people, 8 are Black men. The Supreme Court simply said the overall percentage disparity has been small. There's no particular reasoning, certainly no quantitative reasoning given for this word small. So a question for you is, the court is saying, yes, 8 in 100 is less than 26%, but it's not enough to show systematic exclusion. And my question to you is, what do you think? Without calculation, what comes to your mind? That seems wrong. In what way wrong? The disparity is too large. 8 is pretty small compared to 26, pretty small compared to 6, too large of a disparity. It's over half a reason. So what you're saying, based on your experience of studying randomness, is that this looks like it's out of line. So what we're going to do is look, actually, that's the end of the story. Why don't we just go to a notebook, which I hope I can find. Here we go. Okay, can you see my notebook? Yeah? All right. So we have a population where 26% were Black and 74% were not. And the panel had 100 people on it. Okay, so our sample size is 100. Now what we're going to do is we're going to say, okay, let's just pretend they drew at random. if we pretend they drew at random, then we can see if we draw at random, what do we get? And so we're going to use sample proportions, and sample proportions takes two arguments. It takes the sample size, and it takes the population from which you are drawing. Name sample size is not defined. If you run the cell, here we go. So in this sample, 21% were Black and 79% were not. Now, in the end, we are going to look at the count of Black jurors in the panel. And so therefore, we'll just look at the first item. And this time, 23% were Black. And I'm going to keep running the cell. And what you're looking for is, do you see an 8%? Anybody? That's 20% right there. Anybody? 8%? Nope. Not 8%. So let's just quickly write a function that returns the number of Black jurors in a simulated sample drawn at random, a simulated panel drawn at random from the eligible population. I'm just converting the proportion to a count here. And so this function will do it once. And then what we'll do is we'll make an empty array for the counts. We'll repeat the process 10,000 times and make and collect the arrays. And someone says histogram time, you bet. So this is the use of the for loop that you have seen over and over again. Start with an empty collection array, run the loop over and over again. Run the loop. So repeat the experiment many, many, many times and keep appending to your collection array every single time. So we'll do this 10,000 times, and actually doesn't take that long. And yes, time for histogram. So we will now visualize. Right. It is important to understand what has been visualized. This distribution, this histogram, represents the counts that we got of Black men in a panel when the panel was selected at random. And you can see what was the proportion in the population. The proportion was 26%. And so, these are sort of centered at around 26%, but they're not exactly 26%. They're a little bit off. Here and there, they're a little bit off. But how far off? I'm saying proportions going from what, about 10, 15 to about 45, and very, very unlikely to be that small and that low. And what is this red dot? Can somebody tell me what that red dot is? It's 8. And why are we putting 8 on this graph? To show how, to show the yes, that was what was chosen. You see, this is our mind game, the blue histogram. It is what would happen had this panel been selected at random, but the red dot is the important thing because the red dot is reality. And what you are seeing in this picture is that the reality and our assumption, the predictions based on our assumption of randomness, do not agree. So that is the picture, and I see this as a visualization of bias. Had the panel been selected at random, then you would have gotten counts that look like what you see in the histogram. The reality, though, for Robert Swain was that the panel contained only 8, and that difference is too large to be explained by chance. You don't need to calculate any chances. You can just see it on the picture, and you have all seen it. But what did the Supreme Court decision say? The Supreme Court decision said that, differences like this, 10, 15% compared to 26%, the overall percentage disparity has been small. Now, that small was some qualitative judgment that may have felt reasonable to the justices at the time, but I want to make the point again that a few weeks into your first data science course, you actually have proof that that was incorrect. I want to pause for a second and take questions. We have powerful tools, and we should use them for good. So, let me just give you some language here. Well, let's just go back. What we've done is essentially a data science calculation. We've done a computation, and we've come up with a result that numerically these two things don't match up. Okay. But in the end, this bias comes from somewhere, and it is really important to understand exactly what was biased. And that is where data science differs from, say, a purely computational field, right? We actually have to go in and look at what was going on. And systemic error, yes, exactly, systemic error. So Robert Swain was not just arguing the unfairness of his own trial. He was saying that if you look back 10 years, you only get counts like 10%, 15%. Only once did you get 23%. Now look at those numbers. If you look at our histogram, 10 and 15 are also hugely unlikely. Any range like that is hugely unlikely. Moreover, every single number that is in the evidence, and the Supreme Court accepted this, is below 26. So the errors are systematically on one side. It's always low. And there's a definition of statistical bias, which is when the errors are systematically in one direction, then the process is biased. But this is not only about statistical bias. Statistical bias came from somewhere. And so I have a question that I'm going to ask you. And first, I want to remind you that the required process, the randomness, was in choosing from all eligible jurors in the county to get to your panel, right? That 100 people was supposed to be selected at random. And now we're going to describe how the selection actually worked. This was actually described by the Supreme Court in its decision. The actual process used was this. The jury commissioners selected the panelists from directories, registration lists, club and church lists, conversations with other persons in the community of all races, and personal and business acquaintances. Now, one of the things that we often ask you to do in discussion questions, and indeed in education throughout, we keep asking you to answer questions. But what I would like today is to simply ask you, look at what was required, look at what actually happened, and tell me what questions this raises in your mind. The commissioners picked their friends. How is that fair? How is that fair is a great question. Other questions that arise. Do these lists disproportionately correspond to people of privilege? Indeed. Club lists. Do these correspond to privilege? What race and economic standing are the commissioners? This is a great question. We are looking in 1960s in Alabama. The commissioners were not Black. Ah, that is a beautiful statement. It sounds like this jury is a jury of the commissioners' peers, not the defendants. What a beautiful comment. Okay, so Eva, how is the process different now? What steps to make sure that this doesn't happen? That is a question I'll try to address in the second example. The jury panel is supposed to represent the eligible jurors. Okay, so many questions have been raised by this, but can I look at this and tell me which community is this biased against? Robert Swain was a Black man. He's saying that his trial is unfair. Who is this biased against? The Black community. Because personal, social and professional circles, those are very much tied to the community where from which you come. And yes, biased against the Black community. And what you're seeing here is racial bias in action, and I will talk about this a little bit more in a bit. So many questions are raised by this, as you can see. There was a second process of jury selection, the eventual selection of 12 people. And from that, all 8 of the Black men who were on the panel were excluded. 2 were excused, they could not serve on the jury. And 6 were simply excluded by a process called peremptory challenges. And this process, lawyers on both sides could exclude a panelist without giving any reason. And what Swain said was that the prosecutors in Talladega County were systematically excluding Black jurors. But the court upheld the process. The court said, no, it has not been proved to be discriminatory. Well, they were wrong. And one of the reasons for studying examples like this is to also note that strength, courage, persistence, especially persistence and strength, leads to improvement. So let me introduce you to the lawyer for Robert Swain. She was Constance Baker Motley, the first African-American woman who argued in the Supreme Court. And she won, except one. She lost Robert Swain's case. Yes, the calculation that we did is being used in cases these days quite routinely. But this case was lost. But somebody else was just about to start on the Supreme Court. And that was Thurgood Marshall. In 2 years, he was appointed the first African-American Supreme Court justice. And he had been studying the Swain case. And he knew that that decision was not sound. And he was working on reforming the laws that about peremptory challenges, which I remind you is where you could just strike somebody, right? Just gone. And after a 20-year struggle, this was, the decision was reversed by Thurgood Marshall and the Supreme Court. And based on what? Based on pretty much exactly what Constance Baker Motley had said in Swain's case in 1965. She got posthumously the Congressional Gold Medal. Now, Thurgood Marshall was not naive. He realized that if you ban peremptory challenge, if you ban challenges based on race alone, then some legal team is going to find some way around it. So he urged the elimination of all peremptory challenges. That has not happened. Our textbook section, this is 11.1, has a long discussion and many references that you can look at to see, to read and to discuss. Okay, so I would like to stop now and take a little bit of a break for your questions. This takes a long time to think about. Data science does not exist as a computational field by itself. Data science is about decision-making. Decision-making is about people. And yes, context. Context is important. It is important for us to understand history. And now I want to give you the second reason why I think these examples are important. The first reason was that you have the technical tools to establish quantitatively bias and discrimination. But I want to discuss why we are talking about the 1960s, right? So all those people who decided that it was fine to select a jury panel based on who the commissioner talked to and who their social acquaintances were, they were coming from a position where that seemed reasonable to them. They were coming from long-standing historic bias and injustice against the Black community to the point where it was almost normalized. Right? And so we are examining their bias from the 21st century perspective. And you, as young people in the 21st century, can quickly see the bias and from where those biases came. So why are we studying this now? It is because questioning assumptions, understanding, facing bias, understanding where it comes from is the first place to go if you are going to change for the better. And it is important for us to understand our own biases. We have to understand where we come from. It is very easy to dismiss people in the past as being biased, racist, and so on. But we, all of us, are informed by our own experience. All of us have limited experience, and it is very important for us when we make decisions, when we make statements, to understand what is normal to us. Because we are not perfect by any means. And we must question our own assumptions, where they come from, how our background affects statements we make about other people. And that responsibility, questioning assumptions, is not only the responsibility of minoritized communities, it is every single person's responsibility. Question everything, including ourselves. Exactly. Beautiful. Question everything, including ourselves, everybody. And questioning takes practice. We aren't all born knowing how to question. So by questioning others, then is a stepping stone for us to start questioning ourselves, and I hope we will question ourselves. I hope we will look at people who are not just like us. Crucially, I hope we will listen with respect to people who are not just like us. And I hope that we will have the determination and what it takes to make positive change. That is the reason for these examples. Now, there has been change. This absolutely egregious racism is maybe not there in jury selection anymore. Things are better, but there are still flaws. And so let me point out the California law. In California, that word representative actually is very specifically defined, shall be selected at random. There's no wishy-washiness. From a source or sources inclusive of a representative cross-section of the population of the area served by the court. That is the law. And so the ACLU in our own county studied the application of that law. So they studied a total of 11 trials in the Alameda County Superior Court, and there were a total of about 1,500 panelists. And what they did was they looked at the entire distribution of ethnicities of the eligible jurors and the panelists. You can see this is very much parallel to what we did in our first example, except now we study ethnicity. We're going to study ethnicity in multiple categories. Let's just look at the data, and then we will start discussing questions that arise. So we're now in Alameda County in 2010, and let me show you the table of the data. These categories, the labels of the categories we have taken from the ACLU report, which is linked in your textbook. Okay, so they classified jurors into 1, 2, 3, 4, 5 groups: Asian Pacific Islanders, Black or African American, Caucasian, Hispanic. Other included panelists that were multiracial and or who did not who declined to provide their information. Okay, and so here once again, the ACLU said here is a distribution of the eligible population, and here is a distribution of the panels. Now those are proportions. Both columns add up to 100%. Take a look. Is it not true that the distribution of the panels just plain looks different from the distribution of the eligible population? What do you think? One person cannot be in 2 ethnicity categories. These are distributions. Each person is in one and only one slot. Yeah, so if you draw the bar chart, you can see the blue is the eligible population, the gold are the actual panels, and you can see in some cases the blue bar and the corresponding gold bar are comparable, and in some cases they are not. In particular, the Black and Hispanic population is underrepresented on the panels. Now, the minute some group is underrepresented, some other group is going to be overrepresented. That is something we are going to look at since both distributions have to add up to 1. And so now, what is the question that arises? Because the law says the panel is supposed to be drawn at random. So what is the question that arises? What is a question that arises? Anybody? Is it due to random chance? Is this random? Why isn't the sample representative? How was the sample done? Could this distribution likely occur at random? Yes. So how likely is this? Exactly. So if I summarize all of those suggestions, they're all saying, well, suppose the panel was selected at random. This is your supposition. This is your, your model. If it was selected at random, then could we get a gold distribution that looks like this? Right, and so what do? Well, we do exactly what we did in the previous example. We simply draw at random. And we know how to draw at random from a categorical distribution. And that is exactly what sample proportions does, right? You provide the distribution you want to sample from right here. You provide the sample size, why 1,453? Because that's how many total panelists there were. And you draw. And boom, you have a panel of randomly selected jurors. And of course, that's a bunch of numbers. It's really hard to look at. So we do the same thing. We capture a random sample and then we draw, we add to our table. And so these are the original data. There's the eligible population. These are the actual panels and there's our random sample. Take a look. What do you see? Anybody? What are you seeing in those columns? Which looks like which? Random is similar to eligible. Exactly. Random looks like eligible. If you draw at random, the sample that you drew at random looks like the eligible population, where we really didn't have that feeling about the actual panels. So let us look at bar charts. The eligible population is dark blue. The random sample is light blue. Do you agree that the light blue bar chart and the dark blue bar chart look very similar? Yeah, so what we are saying is that in this particular random sample that we have, the two are very similar. It's very similar to the eligible population, but that is absolutely not the case with the actual panels. And as many people have noticed, there is an underrepresentation of the Black and Hispanic populations in the panels. Now, for a little while, we are going to do a numerical calculation, but then at the end, and it's going to be on Wednesday, we're going to come back and look at what led to these discrepancies. But first, let's just see. If you sample at random, can you get such a difference? Now, notice that this bar chart is the result of just one random sample. If we're going to do this 10,000 times, what are we going to see? Well, we're going to see 10,000 such bar charts, and that's going to be really hard for us to interpret ourselves. And so what we're going to need is a way to quantify the distance between two distributions. We know how to quantify the distance between two numbers, right? You take the difference and take the absolute value, and you've got the difference. But how do you quantify the distance between two distributions? You have several different ethnicities, you have categorical distribution. We need a measure of the distance. And so let's just look at these two distributions. There is a blue distribution and a gold distribution. They're different from each other. To measure how different they are from each other, surely a very natural thing is to just do a minus, right? You have a blue percent here and you have a gold percent here, or a blue proportion and a gold proportion, just do a minus. So let's just do a minus. So here we are, we've done a minus. And you can see that some of the differences are negative and some of the differences are positive. Why? We are doing gold minus blue, right? Panels minus eligible. So we are looking at how much the gold bars exceed the blue. So when the gold bar is actually bigger, we get a plus difference. When the gold bar is smaller, we get a minus difference. Now I want you to look at the plus differences. 0.11 and 0.03, when you add them up, what do you get? 114? Yeah? Can somebody please add the negative differences, see what you get? What'd you get? Minus 0.14, quite. And what you are seeing is that the amount by which the gold bars exceed the blue is exactly the same as the amount by which the blue bars exceed the gold. Because why? Because both are distributions, they add up to 100%, they both add up to 1. And so in fact, the measure of the distance is actually the 0.14, right? The minus 0.14 just has to be true once you've got the plus 0.14. So what we do is we just look at the differences without the minus signs. And if we add the whole lot up, what are we going to get? We're going to get the 0.14. And then what are we going to get? We're not done. What else are we going to get? If we add up the absolute values, you can just add if you want. What'd you get? 0.28, exactly. You're going to get both sets, but really only one matters. So we are going to add up all the absolute values and divide by 2, and we get our 0.14. Now you might be wondering, why don't I just find which ones were positive and just add those? You could, but this is faster. All good? This quantity is called the total variation distance between the two distributions. It is a measure of how far one distribution is from another. And what I want to do is quickly just write a function that calculates this distance. So you give a distribution 1 as an array, you give a distribution 2 as an array. These two are the distributions you want to compare. And you look at the difference, you compute the absolute value, you add up, and then you divide by 2. So you return the total variation distance between the two distributions. And what I want to check is that this thing that we wrote, does it give us the 0.14 that we got in the comparing the panels and the eligible population? It does. That is a relief. Now, tell me, if I took a random sample, looked at its distribution, and computed its distance from the eligible population, do you think the answer would be bigger than 0.14 or less than 0.14? Do you think it would be a bigger distance or a smaller distance if you compare the random sample? Smaller distance. Well, let's just see. Okay, so here what we are doing is we are taking a random sample, and by using sample proportion, we get a sample distribution, and we calculate the total variation distance between this random sample distribution and our eligible population. I run this cell, and what do I get? I get 0.015, about 1/10 of the distance that I got before. And I'm hearing the Campanile, and I'm just going to run this cell a few times. I'm going to keep running the cell. What are you saying? It's about 0.02. 0.01, 0.02. Are you saying a 0.14? Anybody? Nope. Very similar situation. Very similar situation to before. Okay, so we will complete this calculation before. Why does it get smaller? The reason is that the total variation distance is a distance between two distributions. So if you look, when you look at the light blue and the dark blue, they're very similar. So the distance between them is small. If you look at the gold and the blue, they are quite different, so the distance is larger. So I will now stop the lecture